To host this workshop. We are very fortunate to have a 10 presentation today. We can hear about outstanding success experience in drilling activity and amazing new drilling technologies. However, there are two things that are not good enough. First, I have poor English. Second, we may have not enough time. There will be no break or snacks. Okay? Therefore, I will try my best to keep myself silent. Secondly, please be punctual when you share your presentation. Each topic will only have 15 minutes, and I will give a reminder after 30 minutes. Please go to the toilet on your own. Thank you again. So let's begin our presentation. The first presentation, we will invite Graciano Emanuelito de la Cruz. Missed. Thank you. Please. Okay, thank you. Hello. This one. Good morning. It's a profound honor to be the first speaker in this morning session of shared interest in geothermal energy and sharing knowledge and experience to everybody. Today, I will be discussing a critical pillar of the geothermal project, which is the organizing an effective drilling team based on the Philippine experience. The Philippines offers a half a century hard-won experience with challenging conditions and lessons learned from the field. So again, I'm Graciano Emanuelito E. de la Cruz III. You can call me Domo. I'm from Thermaprime Drilling from the Philippines. First, let me introduce our company. Now, Thermaprime can actually trace its history back to EDC, Philippine National Oil Corporation, Energy Development Corporation. It's government-owned, designed to actually develop the indigenous energy of the Philippines during the 1970s energy crisis. We evolved from a government-owned company into an individual, independent, service-oriented drilling contractor. And now we have a fleet of rigs from 1,000 to 2,000 horsepower, designed for the rigors of drilling in the Philippines. For today, the agenda we'll be reviewing the geothermal value chain, where the drilling team will be coming in, typical drilling conditions in the Philippines, the rig selections that we do, typical well pad setup, well site drilling team, the KSA of the drilling team, service providers, drilling capability, and our closing remarks. Before we build the drilling team, we must understand first the geothermal life cycle. This is the life cycle. Oops, sorry. So from geoscientific exploration to, steam field development up to the sustainable production. Drilling is actually in the exploration, and also the bulk of the work is actually in steam field development. Now, if we look into the value chain of our well design, we can see that the drilling team is actively involved in drilling and completion. For construction of production and reinjection wells. For the maintenance, it's going to be workover, depends on the problem that you will have. and then eventually plug and abandon. Now, let's look at the Philippine condition. Typically, the Philippines would drill 2,000 to 3,000 meters depth, and with high temperature, high quality resource, we actually intersect multiple faults. We have high abundant expanding clays, the smectite, known acid zones, and there is actually mature geothermal, highly fractured fields. We also use utility scale geothermal development in which we have to drill several or many well designs. And because the Philippines is an archipelago and the equipment is imported, we have problems with our service support. Now, these operating conditions results to complexities. The well design is complex, drilling strategies are hard, then formations are, data of the formation sometimes is not available, there is total loss almost always present, there's also persistent collapsing formation in which it can lead to stack pipe or eventually abandonment. Now again, with the support, there's going to be high cost on capital investment for the infrastructure and also for the inventory. And we have to remember that every well is different from each other. So there's no two wells that will have the same conditions. Now, after the well design and the conditions known in your field, the next hurdle is actually rig selection. You have to know that the rig can do rotary drilling, circulation, pipe handling, well control, and then there are factors to select your rig. What's the maximum depth? What's the maximum pull? The tools that you will be running in, the bit, the bottom home assembly, the motors, and everything. And also, it has to overcome the pressures and also the flow rates that is needed. And in some cases, in some contracts, the rig is actually involved in cementing. It has to have its own cementing package. It has to have its own directional drilling tools, but just for basic drilling. The table below is actually a configuration of the classification of the rig based on IADC. Now, let's look at a typical well pad in the Philippines. This is rig 7 in the Philippines. It's in Tiwi Albay. As you can see, it is a very complex ecosystem in which you have the rig components, the top drive, the mast, the draw works. It integrates with other equipment from the service providers like the air drilling services, drilling fluids, directional drilling, cementing, and also the developer's equipment. There are some equipment there. If there are already pads or wells that are existing, so you have to adjust your well pad, considering all the pipelines also. Now, what are the important things here? As you can see, the rig is not alone. So, this is where your drilling team comes in. This is the core of our discussion. So, as you can see, this is a typical drilling team that you have. You have your developer, in which you have the drilling engineers, your drilling supervisors. You have your contractors. These are the third-party contractors. The first is the rig contractor. So, it's under the rig manager, and then you have your tool pusher, driller, assistant driller, rouseabouts, and at this one, sorry, these are the support groups. Sometimes you cannot see it in the well site, but they are the support groups, the maintenance, the camp support, logistics. But this, the central part of our team is actually on the rig. Now, the drilling team has its own knowledge, skills, and abilities. Each position has its own technical knowledge that it has. He has to know also the laws involved in the sites that they have, the local laws, labor laws, everything. And also technical knowledge about the equipment, like the driller, you have to know how to operate the console and the draw works. But for us, in Thermoprime, safety is paramount. So each person on the rig has the ability to stop work or the stop work authority. If he finds any imminent danger, he can stop the work. This is to foster safety culture. Now, again, the rig crew is not alone in this work because of the complexities and the risk and the challenges of geothermal drilling, we have our friends from cementing, our friends from directional, our partners in drilling fluids, air drilling. If there's workover, you can have fishing, then logging also, cement band logs and everything. And there are other contractors that you actually hire for special works in the drilling pad. Now, these are some of the risks that actually are important in overcoming the problems that we have in the well site. The first one is extreme heat. So if you have extreme heat, your drilling tools must be designed or good adapt to that temperature. Corrosive fluids, that's for mud engineering. You have total loss circulation, air drilling can help you there. Then the wellbore integrity, cementing can also help. So all of this, it has to be integrated in your team. It has to work with the drilling supervisor, the rig manager, and all of the supervisor of the services. Now, what are the attributes of a competent drilling team? They have to have a strong background in drilling engineering. They have to be experienced also in geothermal drilling, especially the contractors. There should be meticulous planning and also continuous monitoring of the performance. We have to always be efficient because every delay is additional cost. Teamwork is also very important. Communication lines in the rig is very important. The accountability and responsibility should be clear. If it's not clear, there's going to be a problem. And the benefits of having all of these attributes is you'll have safer drilling, efficient drilling, minimum formation problems or formation damage, your non-productive time will be reduced, and ultimately the cost of the well will be lower. And if it's lower, the wells that you can drill will have, let's say, several more wells for savings. And you will have an earlier power plant commissioning and higher profits. Now, success through integration. We talked about the rig, we talked about the contractors, the service contractors, and the team, and the life cycle. You have to integrate all of them to have a successful campaign. So, we always look at the life cycle of your geothermal project. That the smooth transition from one node to another will be the more effective process. So you optimize your operational complexities, the challenges you have in the well pad, and then the team has to be a one-team advantage or one-team mindset in the rig. Ultimately, you have to have your selection of equipment fit for purpose. You have to consider your local geology, your local support, your local service contractors. So that it's not always cheap drilling. Because sometimes, cheap drilling is actually a more expensive problem. So lastly, in closing, the Philippines actually adopted oil and gas standards and also lessons learned from Iceland, from New Zealand, and other geothermal countries, and implementing it into a proven, successful drilling project. Now, Taiwan, moving forward, must adopt these standards selectively. You have to select your own so that in the near future, you can achieve your geothermal dreams. So with that, thank you, and let's connect. Hopefully, we can talk later. So that's all. Thank you.
Thank you. We still have some time, so if you have question, only you can just one question, please.
Yes, sir.
Sir, sorry, I have one question. What's the how about the distance between the injection well and the production well? For example, in Philippines, the common distance.
Usually, it's about 250 meters, sir. No.
I'd like to answer that question. I'm Manny Ojena. I'm the Senior Advisor of under the Office of the President of Thermal Prime. I have 38 years of experience in geothermal since 1979 up to my retirement in 2016. Okay, so I can answer your question. In the Philippines, it actually depends on the complexity of the fractures in the rock formations. But minimum, we cite reinjection sector from the production sector at about 1 kilometer. This is on a pad-to-pad basis. But the reinjection well actually are deviated away from the production. Okay, and there should be between reinjection wells, the production, the injection sector, and the injection area within each individual should be at least 500 meters. Same as in production, because there will be interference, there will be sharing of production if you have less than 500 meters. And therefore, with sharing, instead of maximizing the output of the wells, say production, you actually is reducing it because they're sharing in the same production zone. I guess that answers your question.
Thank you. From this presentation, we have a clear blueprint. And then let's continue next is a directional drilling key to developing geothermal in Taiwan. Welcome Ken Wei Chen, Mr. Ken Wei Chen. Thank you.
Okay, there's a delay. Okay. Okay, good morning, everyone. I hope you're not bored seeing me again. So I've been attending too many talks. So while we are waiting for it, so today I'll talk a little bit on why we talk about developing geothermal in Taiwan, right? So one of the things that Dr. Bill from CPC talked about on the stage, there are the challenges that we are facing. One of them is the footprint that we have. We have limited space for the well pad, the space to develop. So we know Taiwan, it's very densely populated. It's very difficult for you to find a large piece of land to build power plant. So directional drilling is one of the things that we can look into to actually venture into different pockets and bring all the heat into one power plant, and then we develop the power from there. So while I'm still waiting for my slide to come up, okay, ma. Okay, so I think without the slides, let me just by memory what's in the slide. So one of the things that we looked into yesterday is also the Tatun Volcano Group, right? The heat source and most of the very, very hot area is located inside the national park. So for my understanding at this current point is that it is not allowed to develop inside of the national park. So one of the things that I was talking to the geothermal single service window. I was talking to Alex. They were saying the government is looking into allowing directional drilling as long it's within, is deeper than a certain depth. Then they allow to drill into the national park. So I think in that case, you can actually see that will actually make developing geothermal much more efficient now. Now, you don't need to actually choose your site and to just drill straight. And drilling directional well is not new. In the oil and gas, we have been doing it for the past how many decades? And to my knowledge, in Halliburton, the longest directional well they have ever drilled is 16 kilometers. Now, thinking of 16 kilometers, 16 kilometers, how far is that? It's probably here to maybe, I think from CPC building to the nearest domestic airport is, I think it's 5 kilometers. And imagine it's 3 times that distance. which means you have excess potential to actually go into much more different heat pockets that you have explored. So which means you can bring all of them into one single pass. And here's my presentation. Thank you very much. So let me go next. So this is just to set the scene. So I try to set the scene to make sure everyone is on the same page. So from academic studies, Taiwan has a lot of deep geothermal potential. So just like oil and gas, the easy pocket, shallow one, it's probably being developed or being found. But the real heat, the real potential are in the deeper part, and they are probably scattered around. So from there, the quickest feasible development target we can see is about 10 gigawatt, right? And the shallow one, if you develop them, is probably just 1 gigawatt max. So looking into that, there is a lot of potential that you can do as long we look into directional drilling. Now, one of the things that I was discussing, I've been to Taiwan for almost a year. We look at, there's a lot of barriers that is actually holding Taiwan back. So one of the things is regulatory constraint. So in the past, as long you go under my land, you need my approval if I'm the landowner. However, if you look at it, how deep is my well? Once you drill a directional well, you're going to start kicking off about at least 1 kilometer depth. So the landowner, sometimes they think, will this affect me? Actually, it doesn't. Because we need to put into perspective, how far is 1 kilometer? Which means if something happens here, I don't think you can hear anything from Taipei 101. Here to Taipei 101 is probably 700 meters. If that, I'm going to give it, if there is a car crash here, which means it's generating a lot of noise, tremble, but people in Taipei 101, they wouldn't know about it. And now looking at drilling, how big is the well bore? So the well bore is even smaller than a car. The well bore is probably this size. And anything happens 1 kilometer away, it's very, very minimal impact to the surface. So I understand now the Taiwan regulation is looking into this to allow, as long at a certain depth, past a certain depth, they don't need to get the approval from the landowner, which this will actually help develop geothermal in Taiwan. Of course, looking into the next one is complex geology. So Taiwan is formed by the collision of two different plates. If you look into the recent deep drilling, even in Yilan province, in the north, where the first deep geothermal well is drilled, Yuanshan number 1, and then now it's drilling Dongshan number 1 well. The two wells are not really that far apart, but the geology changes drastically. So which means understanding of the subsurface, planning of a well, the design is very critical. And currently, of course, limited drilling capacity in Taiwan. A lot of the wells are drilled just well below 2,000. So a much more heavier rig is required to go deeper and further. So I really enjoyed the Thermal Prime's presentation. That is where you bring expertise from overseas, where they have done a lot of deep drilling to actually help together to grow the geothermal in Taiwan. So now I talk about the challenges. Now we want to answer why directional drilling. So this is an AI generated image, but the idea is you are reaching different pockets to bring all the resource back to just one pad and just build one power plant for it. And one of the things that I see in 2026 is the latest feed-in tariff, 的最新的那个费率. So you combine in previous time it was 2 megawatts and below are considered a different feed tariff. Higher than 2 megawatts is the feed tariff, but now it's 5 megawatts, which means the government is encouraging the smaller geothermal players to work together to build a bigger power plant, to co-develop an area instead of everyone building their power plant in silo. So here, by directional drilling, you can reach multiple zones. Your pocket might be here. There's another pocket probably below. From one pad, you can reach different pockets. Then you can reach beyond your property boundaries, which means I just need to get my land here to build my power plant. But my heat source might be from that part of the area, another part of that area. By directional drilling, as long allowed by regulation, I can reach that pocket. As long it's deeper than a certain meters depth, probably 500 meters depth or 1,000 meters depth. It depends on the Taiwan's regulation. So I will not comment on that. Then you can optimize your trajectory. So which means you can design a well. Instead of straight well, you optimize one well to reach different pockets to bring all the production to your power plant. Then, of course, the important one is reduce footprint. So Dr. Bill, yesterday, he talked about, there's limited land. So all you need to do is to develop here where I'm standing, but I can reach every pocket far from me. Now, of course, challenging terrain. So Taiwan is hilly in some part of the place. Sometimes you can't really find flat land to actually bring a big rig in. But if you have directional drilling capability, you can find an optimal flat land, but you can reach that pocket using directional drilling. So that's the message that I want to bring today. So this is just a very quick, I try to keep marketing slides to the minimal. This is one of the offerings that we offer from our Halliburton drilling department. We call it SDS, battery drilling services. So we provide directional drilling, logging well LWD, MWD. We also provide digital optimization, which everything is digitalized, is connected upwards. We have automation, drilling. We have all these services actually to help you to drill to your target much more efficiently. So I think this is my last slide. So a very quick introduction on what we offer in directional drilling is that, of course, we have what we call our iCruise intelligent RSS rotary system. So this helps directional steering of your well. We have our Logix automated drilling. This is quite interesting where everything is computer automated. It looks into a well plan. It looks ahead of the drilling, feed it back to the system. If anything, you can actually help to actually steer your well bore. Then, of course, we have mud motors to actually help steering it. I think one of the interesting one is what I want to introduce is at the end here, which is EarthStar, our ultra deep reading resistivity. So what this does is that in front of the drill bit, there is a deep resistivity electromagnetic reader. So what it does is that it tries to read what's ahead of what you are drilling. This is very important, especially when you are drilling in new frontier areas. You may have your conceptual model being built. You may have a lot of subsurface data being acquired. But there is always a saying we have always in oil and gas. All models are wrong, but some models are useful. And you never know until you drill. You can say that this data it shows certain things, certain features, certain geology. Until you drill it, you can never be sure. So here it helps you de-risk your drilling. It looks ahead. If it detects something that is a really anomalous reading compared to your geo model, then you can call it a stop or you can steer it away. So this is one of the things that what we are very proud of. It's to look ahead using electromagnetic through our EarthStar. I think this should be my last few slides. So there are also other things that we have, like one of the things that we look into Tatun Volcano Mountain, it's we are going to drill into high heat zone. So this is what we want, but at the same time, because you are using directional drilling, there's a lot of electronic tools that you need to make sure that it qualifies for high heat drilling. That's very, very important, so that you make sure that it's we make sure that our tools are durable and give you the best performance so that you can achieve your directional drilling, number one, quick, number two, safely. So I think that's it from me, a very quick introduction. I think my key message is here. Directional drilling, it's a game changer for Taiwan geothermal development. You limit the space that you need, but you reach maximum geothermal development. Thank you.
Thank you, Mr. Tan. We can ask one question. Yeah.
Oh yes, let's this.
How many jobs you have done for the high temperature training? How many in the world you have done?
It's a very difficult question for me to answer, but I will just very quickly say, Halliburton is the main integrated service provider for the largest geothermal project in Indonesia, which is the Sarula project. So we handled the drilling, we handled the well design, we handled the logistic and everything. So we delivered about 300 megawatts of wells worth of power in the span of 2 years. So if you ask how many wells we have drilled, I don't really have that number at my fingertips, but from what I have in my slide yesterday, we are involved in 400, we drilled more than 400 geothermal wells in Indonesia. We are also involved in Philippines, we work a lot in Japan. So I would say not only high heat, high temperature is found in geothermal. In oil and gas, well, we do have that experience as well, handling high temperature and high heat. So I can say Halliburton is ready to actually help Taiwan to accelerate your geothermal development.
Thank you, Mr. Tan. It's Mr. Yonglek Ka is here. Thank you. Welcome to the next presentation. Smart Drilling Transforming Geothermal Exploration through Optimization. Thank you.
Yes. Hello. Yeah. Good morning, everyone. It's a privilege to be here to join you at this year Taiwan International Geothermal Conference. Today, I'll be sharing how Baker Hughes is transforming the geothermal exploration through optimization, both in the bottom hole assembly and across the digital ecosystem. So we will look at the evolution of Baker Hughes RSS and LWD service, and then dive into this latest breakthrough, the TruSteer RSS system, and the Cantory digital platform. Cantory digital platform has just win this 2026 offshore technology conference, the Spotlight on New Technology Award. And then, so Baker Hughes drilling heritage stretches back to the 1970s, when Eastman, Christensen, and Tedico reshaped the industry with early directional drilling and MWD technologies. So these were the innovation that first allowed operators to think beyond vertical wells and explore more complex subsurface targets. In the early 1990s, Baker Hughes brought this pioneer together to form Intact. That momentum led to defining milestone in 1997 with the launch of first AutoTrack. The AutoTrack did not just improve drilling, it transformed it, setting a new industry standard for directional control and wellbore qualities. Fast forward to 2019, when we introduced the iTrack Intelligence drilling system, bringing digital intelligence and real-time decision-making into the drilling business. In 2020, we advanced again with the Lucida Next Generation RSS and the Duramax Moto. And now in 2026, Baker Hughes introduced True Steer. This is a new pinnacle in our RSS. So yeah. Our logging while drilling journey follow a similar path of innovation. The legacy of Western Atlas wireline logging is the foundation of our LWD development, which began as early as 1978. By the early 2000s, the industry shift towards high-angle and horizontal wells create a new demands for real-time formation evaluation. Baker Hughes transformed its mature wireline expertise into a full suite of LWD technology. In 2020, we integrated and upgraded these tools into the Lucida platform. At the same time, our digital evolution accelerated. iTrack for real-time decision support, Dual Suite for advanced modeling, CORWA for operational analytical, and now Cantori, our next step towards a fully connected intelligence drilling ecosystem. Together, these advancements show a clear trajectory from traditional measurement to integrated digital platform, and from new raw data to smarter, more automated drilling decision. With that foundation in place, let's move into the next breakthrough in drilling performance, the True Steer rotary steerable system. Before that, let me introduce the Baker Hughes directional drilling technologies. In Baker Hughes, we have a comprehensive directional drilling portfolio in the industry. On the model side, our NaviDrill Ultra family covers everything from standard directional work to the toughest environments. That includes Ultra, Ultra Curve, Extreme Series, and Duramax, which deliver exceptional torque and power for long, abrasive, and high temperature section. Our rotary steerable portfolio is just as deep. For decades, AutoTrack has set the benchmark for smooth, precise, continuous steering, starting with AutoTrack Express, AutoTrack G3, AutoTrack Extreme, AutoTrack Curve, and AutoTrack Exact. We also offer Lucida, our advanced proportional steering RSS, and now True Steer, our latest evolution in automated wellbore placement. For vertical section, there's AutoTrack V, and for specialized work, we have CoilTrack and SureTrack. This breadth is not just about having tools, it's about delivering the right combination of motor, RSS, and automation to maximum ROP, improve wellbore quality, and reduce drilling time. Our rotary steerable evolution tells a clear story of continuous improvement. AutoTrack G3 introduced gravity two-phase, a modular design, continuous proportional steering, near beat inclination, and 2D inclination hold mode. AutoTrack Curve and AutoTrack Exact expanded those capabilities with magnetic two-phase, high build rate, near beat vibration sensing, and full 3D inclination and azimuth hold mode. And Lucida advanced the platform further with high temperature electronics, near beat torque and weight on beat measurement, and MCM electronics designed for extreme environments. Now, True Steer carry all the advanced feature of Lucida with added HFTO dampening, high frequency torsional oscillation for superior stability in harsh condition and environment. So from G3 to True Steer, our mission has remained constant, deliver better control, better data, and better wells. As the drilling industry now push into deeper, hotter, and harder formations, one challenge has emerged as a major barrier to predictable drilling performance, the HFTO, high frequency torsional oscillation. HFTO is one of the most destructive form of drilling dysfunction. It accelerates bit wear, fatigue, BHA components, shorten tool life, and leads to premature failure and unplanned trips. True steer paired with the permafrost true drill bit delivers predictable peak performance in harshest environment. Its advanced design neutralizes drilling dysfunction at the source, while the bit is engineered specifically for RSS efficiency and durability. So this is the case study from North American land, one of that clearly demonstrate how the right steering technology can overcome drilling dysfunction and unlock higher performance. The results were immediate and impressive. With Cruise Steer, the team achieved a 15% increase in weight on bit, a critical factor in improving ROP, and more importantly, HFTO was virtually eliminated. By stabilizing the drilling environment, Cruise Steer unlocked performance that simply wasn't achievable with the previous setup. This improvement doesn't just reflect better tool design, it reflects a shift in drilling strategy. When HFTO is controlled, operator can push parameter harder, drill faster, and reduce non-productive time. And another drilling campaign in Northeast United States, 5 horizontal wells were drilled under similar conditions, 4 with conventional RSS and 1 with Cruise Steer. The results were remarkable. The lateral ROP had been increased up to 60%, and the distance drilled in 24 hours and 48 hours has been significantly increased as well. So in the same campaign, the well drilled with conventional RSS struggled with HFTO, which led to performance degradation and reliability issues, even with third-party dampener. When Cruise Steer was deployed on the next well, HFTO disappeared. The system handled higher weight on bit, deliver higher ROP, and show clear potential for even better performance in future runs. This is the difference that advanced steering technology makes. Our high temperature rotary steerable system are designed to operate up to 175 degrees C. And with the right drilling optimization, we can safely deploy this tool in environment hotter than their nominal rating. So now let's shift to the digital side of the equation, Centauri. Centauri is our platform for autonomous well construction and is built on 4 key pillars: real-time branded intelligence. We combine physics-based model with adaptive AI to deliver predictive insight at edge, fast, accurate, and actionable. And the second one, cyber-physical interface. Centauri connects directly with rigs, system, and backend tools, enabling closed-loop autonomous drilling control. The third, an edge cloud hybrid architecture. This gives us ultra-secure, low-latency automation that can run remotely, reliably, and at scale. And the final one, the digital partnership. We work with major technology providers to accelerate innovation and ensure interoperability. Centauri. This slide shows how Centauri is driving down well delivery costs, increasing production, and lowering emission for our customer. So Centauri reduced the invisible lost time, ILT by improving crew-to-crew consistency, optimizing tripping, and speeding up section cleanup. It increased ROP by advising and controlling surface RPM. Then on the prevent MPT side, it prevented by preventing tube failures, avoiding stuck pipe, and reducing hole collapse risk. And it improved reservoir placement through autonomous navigation on this increased production side. So here, the case study from Equinor, the Canterbury delivered a 29% improvement in gross RP. Before the automation, the average RP was 35 meter per hour. And after automation, it jumps up to 45 meter per hour. This is the case in Algeria. Canterbury delivered a 26% improvement in RP and 37% reduction in weight-to-weight time. Canterbury optimized weight on bit and RPM in this case, and minimized vibration and improved hull cleaning, while COA provided visualization to track improvement and ensure consistency. In Argentina, Total Energy managed to reduce the well delivery times from 7.7 days to as low as 5.1 days using Lucida, iTrack, RCS, Permafrost, and Canterbury. This is the power of combining advanced drilling tool with digital automation. So here's are the highlights extracted from SPE published case history that show how Canterbury-driven automation is reshaping drilling performance around the world. Across all these SPE documented projects, the message is remarkably consistent. When automation, real-time intelligence, and human expertise comes together, drilling becomes faster, safer, and far more predictable. They represent a true step change in how well are delivered globally. So thank you.
Thanks, Mr. Yongdika, and have a smart drink puppy. And we don't have time, so everybody be smart. Memorize his face. If you have question, please ask him on your own. And that's next, geothermal system for remote communication. Please, Mr. Yongjue Yuan. Thank you.
Hello, good morning, everyone. My name is Wanju Yuan. I'm a research scientist with the Geological Survey of Canada. I'm so happy to be here to join this workshop and learn from you experts about the drilling technologies for geothermal development. And I'm a reservoir engineer by training, and most of my colleagues are in the geoscience areas. So our work is mostly not that directly related to the drilling technologies, but all our works is finally have the same purpose to reduce the exploration and the drilling risks. So today, the title of my talk is Geothermal Systems for Remote Communities, De-risking the Exploration and Drilling through the Interdisciplinary Studies. Here is some background. My colleague Steve yesterday introduced that Canada is a vast country, and also, however, it still has over 200 remote communities that is not connected to the national grid systems. So especially for the north region, most of the communities heavily rely on the imported diesel for both electricity and heat demand. And with the increasing need for energy security and sustainability, that reliable, clean, and sustainable energy is needed to provide not only electricity, but also might be more important for Canada to provide the heat demand to offset the diesel carbon footprint. And also we need that energy is dispatchable, not only for day and night, but also can handle the varied seasons over the year. And also, what is more important is it should be like local generated. We don't need to import any other energies to that communities. Some background that geothermal turns out is ideal promising resources can meet those requirements. And we did comprehensive resources potential assessment. Steve also mentioned in yesterday's meetings. And here on the left is geothermal heat flow across the countries. And Canada has a variety of the different types of the geothermal resources. And what I want to emphasize here is the wide area doesn't mean that there's no resources, but we lack the enough data, or the data is too sparse to fill the gap. But to fill the gap, there's a lot of challenges. For example, that especially for the north regions, the logistics is very costly. That we, even for the field work or the drilling campaigns, that we usually need the aircraft to move our camps, to move our peoples and the gears. It's very costly. And also, Canada has various terrains across the country, including the mountains, forests, the wetlands, and the extensive permafrost. So most of the areas not that easily accessible. And also for the weather, we have a very harsh climate, especially for the north. We may have only 1 month or 3 months to 3 months time window to do the field work. Here's a photo that we do the field work last summer. It actually is in the mid-July, so you can see that we very short time for the field work. Now, of course, you need to always be alert by the cube buddies around you when you do the field work. And for the resource assessment, we mainly rely on the data in the geoscience, like including the geophysics, geochemistry, and hydrophysics. If we have the core, or have the well drilled there. But for the remote communities, or most of the area has never been studied for the geothermal resources. So data is very, very limited. Well, for the past 5 years, we try to find new ways to efficiently screening the high potential area by using other disciplinaries. So we end up using remote sensing and also reservoir modeling to help us narrow down the possible areas, and before you dedicate a very detailed geophysical survey. Here is I first talk about the remote sensing. The first sensor we use actually is a temperature probe. It has the 10 centimeters long, and the temperature sensor is in the button. You can program it to record the environment temperature at a certain time intervals. And then we bury those temperature probe into in the same site for 2 different depths. One is near the surface, one is much deeper. So you have the same, you have record the temperature for those 2 sites. You have the temperature difference, and then we measure the thermal conductivity in between, and then you can roughly calculate the heat flow in that regions. And then you distribute all those sites to the area of interest. Here is the map we did it in the Mount Meager, which is a volcanic belt system in the west coast of Canada. And you can distribute those stations into the area you have interest, like near the hot spring or near the fault regions or the linearment areas, so that spread that. And here's what the data look like on the top left figures. That the data shows from the four season. Winter season is flat temperatures, and then goes to spring and summer. So for the flat region, which is in winter, because we have at that period we have the snow cover, what we call is the snow curtain period. So you can treat the snow layer as the insulation that reject the solar radiation and only reflect the signals from the deep earth. So using that data, we can analyze this geothermal anomalies area, which is shows in the on the right top, and it is well aligned with the geothermal anomaly area interpreted with the MT survey. So which is the data is great. So the problem is that we need to have 2 season field works and wait for a whole year to retrieve all the data. So we want to see if there are any sensors we can actually see where it's hot and where is the hot area. So we come up with the thermal infrared cameras to help us to see where it's hot. So we started this work by using a handheld camera in the field campaign to take picture to see where it's hot. So this is also in the volcanical 1 meter volcanic system areas. You can see that the geothermal anomaly, like the representing by the hot springs, hot creeks, or the heated ground, can be clearly show up in the thermal images. But we took those pictures by took off the helicopter door of my side, fastened my belt, stretched half of my body out, and took those pictures from like 300 meters high elevations. So it is a cool experience, but not always a sustainable way to do it every time. So we further use a drone with the equipped with the thermal camera to do this job for us. The results is good when the temperature is cool. The heated ground can be clearly show up. However, for some area in the summertime, the geothermal or the thermal anomaly in the thermal images show up is not represent the true geothermal, because some bare land in the noon time that exhibit higher temperature than the thermal spring. So, but the problem is we cannot revisit this site as we want. So we want something or someone can revisit the site and take the thermal picture for us. So that's come up with, and we ended up with using the satellite image data to do the interpretations. And then we first apply the satellite image interpretation in 1 meter, also in 1 meter area to validate the methodologies. So from the final process, the thermal imagery, we detect 4 types of the thermal anomaly area. The first one is the obvious surface anomaly showed by representing by the hot springs, and the second one is on the underground geothermal anomalies validated by the MT survey, and another third one is in the north, which is the shallow heat anomalies caused possibly by the landslides. And the first one is the anthropogenic activities such as quarries, road constructions, and hydropower generations, so which the results was great. We further extended this application to many northern remote communities. We visit 15 remote communities last year and collect thousands of satellite images and process them. All the work can be done within 1 month or 2 months by a master student. So it's a very efficient way to screening out the high potential areas by using the remote sensing technologies. And then we go to the reservoir modeling, that in some area we have very limited data. We have basic geology, but we want to know that whether this area has the potential to provide enough heat. So we come up with using the reservoir modeling. Like for this example, is the Resolute Bay in the Cornwallis Island in Canadian Arctic regions. In this island, we only have 2 wells drilled, and with the basic geology map. So we do this analysis as a reverse or inverse way. We first identify what is the true heat need in these regions, and then we assume some basic geothermal production ways, like the doublet well system or closed loop systems. By doing that, we simulate thousands of simulations to figure out the thresholds for the host reservoir layers, such as the porosity, permeabilities, and the interval thickness at the different depths. So by doing that, we know that at least what kind of the reservoir we need to find to feed this heat demand. And then we're going back to the very limited data, which is 2 wells, well logs, to see if those regions actually have those possible candidates, layers or intervals can provide such amount of the heat. So if they do, yeah, which is good, we can go into the next steps to have more detailed works to interpretate the true permeable zoom connectivities, or even drill the well, perforate to that layer to test the connections. If not, yeah, maybe we should be very cautious to continue to do this work, so that will save a lot of exploration and pilot wells drilling cost. So that is why we think this modeling can help you to reduce the risks. And as a conclusion, I will skip that because of time. And one last thing is I want to let everyone know that the World Geothermal Congress will be held in Calgary, Canada this June. So very welcome everyone to come to Canada to share your stories, to meet your global peers and listen to others' stories. And yeah, welcome to this beautiful city in the foothill of Rocky Mountain. Thank you so much.
Thanks, Ms. Wang Jueyuan. And we can ask a question. Thank you. One question. Okay, thank you.
Yeah.
Because
Thank you.
remove is very, very new idea, I think. So
Thank you.
we can next Mr. Yoshifumi Imamura is here. Thank you. So let's continue the integrating geoscience knowledge for Japan, New Zealand, and Taiwan to advance geothermal development in Taiwan. Thank you.
Thank you. Kia ora, konnichiwa, ni hao, and good morning, everyone. Today, I'd like to share a perspective that connects New Zealand, Japan, and Taiwan through geothermal science. Rather than focusing only on technology, I'd like to start with a simple idea, which is geothermal is not just developed, it is managed. The idea was clearly presented by my colleague, my teammate in Earth Sciences New Zealand, Dr. Andrew Ray, at the conference 2 years ago. I'd like to briefly start from his message and then build on it. Andrew Ray's message was simple. This is Andrew Ray, by the way. I think you know him. Understand the system before development and manage it over time. Geothermal development is management over time. I'm repeating. Geothermal development is management. This is what Andrew Ray said in the last presentation 2 years ago. And if you are interested in his presentation, I brought this 20 copies. So please come to me after this session. Entire session. I'm with this orange envelope, so please come to me. And understanding in New Zealand, we use data and models to guide decisions. And this is what Andrew Ray said, sorry. And before we move into the main topic, I'd like to briefly share an important update, the change of our brand. 2 years ago, after Andrew Ray made this presentation, we changed our brand from GNS Science to this one.
Science begins with a drive to discover, to learn, to protect. We strive to understand the powerful forces shaping our planet. From deep beneath our feet, we rivers and oceans, and to the edge of space, we make sense of our changing world. Now, we unite that purpose to power a better future. Earth Sciences New Zealand, advancing science together.
Yeah, since last year, 2025 July, we have merged with the other research institute, New Zealand Research Institute, called NIWA, and GNS became Earth Sciences New Zealand now. And with a more integrated system, and including now we have water, which are closely connected to geothermal, and in simple terms, we bring together different expertise to understand the systems and manage it better. And I briefly cover three areas. This is what Earth Sciences New Zealand are covering for our research, but mainly three areas are important: geology, New Zealand expertise, and how we can collaborate moving forward. But first, I quickly introduce myself, sorry. My name is Yoshifumi Imamura. I'm apparently Japanese, but working for New Zealand Research, Crown Research Institute. I have been working between Japan and New Zealand for a past decade, 12 years actually, and recently relocated to New Zealand. I live in New Zealand as business development manager, international. And my role is to connect Earth science expertise with partners across the region, including Taiwan. Over the past 12 years, I have worked closely with government and industry partners in Japan, based in Tokyo, and supporting collaboration in geothermal development. The shared tectonics realities, Japan, Taiwan, and New Zealand, all parts are Pacific Ring of Fire. Let me summarize this simply. Japan, Taiwan, and New Zealand all sit on the Pacific Ring of Fire, where tectonic plates meet and move. So we all experience earthquakes, volcanoes, and widespread geothermal activity. This gives us rich understand resources, but also significant challenges. And this is why geothermal is such an important opportunity for all of us. New Zealand has over 65 years of experience, and the success of Wairakei, New Zealand Wairakei, in 1958 came about 8 years before Japan. New Zealand's success was earlier and faster than Japan, 1958. More importantly, it introduced the steam water separator system, which made it simple to generate electricity from water-dominated reservoirs. This is highly relevant because countries like Japan and Taiwan have similar systems. What I mean is, I understand the world's first geothermal power plant was Italy, but we couldn't be successful geothermal power plant because of this kind of water domination. And Japan and New Zealand and Taiwan comes with these waters. Success of New Zealand, Japan can be, these experience may offer useful lessons for Taiwan, like what Japan learned from New Zealand. And here, let me summarize the key challenges in Taiwan. Andrew Ray, and myself believes these are challenges. There are three main areas, again three. First, fluid chemistry. many systems are associated with active volcanism, and the fluids can be highly acidic, which leads to corrosion issues. And second, in the center, geological complexity. Many resources are in orogenic settings with strong structure controls, so the reservoir is more difficult to predict. And the third, scaling. Minerals scaling, such as calcite and silica, can reduce well and plant performance. So overall, they are not simple systems. Taiwanese system is not simple. They require a strong understanding of chemistry, geology, and reservoir behavior together. Yeah, like our previous presentation, as Dr. Yuan said, many challenges in Taiwan. But Earth Science New Zealand, our research institute, has multidisciplinary geothermal expertise like this. Geothermal requires multidisciplinaries working together. And behind this is a team like ours. And this is Earth Sciences New Zealand in practice. So how Earth Sciences New Zealand can contribute to Taiwan? We combine experiments, modeling, and field experience to support better decisions. We can support your decisions. For this geothermal development, I understand we need very high cost drilling cost, for drilling company. But we can support these decision makings by the team. This is what I want to say. And our experience in Japan, as I said, I had been working for Japan as Japan country manager for Earth Sciences New Zealand for the last 3 years. And in Japan, we have worked for actually over 30 years. So I was in Japan for 3 years, but Earth Sciences New Zealand in general had been working for Japan for 30 years, and they are the customers we are working for. And this is a testimony. And let me bring this together. Taiwan, Japan, and New Zealand each have different strengths, but we are working on the same system. New Zealand brings long-term development experience, and Japan brings advanced and innovative technologies, which Earth Sciences New Zealand has been working for the last 30 years. And Taiwan brings new opportunities to innovative by addressing real changes. And by working together, all of us working together, we can accelerate learning and reduce development risk. So to conclude, geothermal development requires strong science collaboration and trust. Earth Science New Zealand have been working with partners in Japan for over 30 years, and more recently in Taiwan. And we will continue this journey as Earth Sciences New Zealand. We hope our experience can be helpful as Taiwan's geothermal sector grows. And we are very happy to work with it. And we look forward to learning together and building long-term partnerships. 谢谢。ありがとう。Thank you very much.
So, thank you, Yoshifumi Imaruma-san. So we can ask a question. Do anyone have a question for this topic? Yes.
Sorry, may I ask one question? The cooperation between the New Zealand, Taiwan, Japan, how is the budget you planning? 1 million, 10 million, something like that, and you have the schedule? I mean, you have a plan, the budget plan.
Hundreds of millions. I'm sorry. We don't have budget. If we develop geothermal, we need to ask you to type for us the same as others, I think. And all of the presenter, I believe, is expecting Taiwan to type for us. But I should say, our science museum, this kind of consulting is very cheap, very, very cheap. Much less than, I'm sorry again, drilling company. Oh, sorry. And our cost is very cheap. I mean, compare with, I'm sorry, drilling company, our cost is cheap. So not $1 million, even $1 million, very cheap, much less than $1 million. Oh, sorry. And also budget is very challenging thing, I think. We easily say we can cooperate, and if I go to government, with my experience, if I go to Japanese government doesn't pay for just New Zealand Research Institute, no. And New Zealand should pay by New Zealand. So this is quite difficult to collaborate if we expect government money, but I hope I'm answering your question. I think the beneficiary who can get benefit, who can get success should pay. And the cost of ours is cheap, much cheaper than others for this drilling. Am I answering your question?
Thanks again. So we go next. The application of geoscience to de-risk geothermal exploration. Welcome, Greg Bignall. Mr. Greg Bignall, thank you.
Good morning, everyone. My name is Greg Bignall. I am a geoscientist. I'm a geologist by training. But today I'm not going to be showing any rocks. I'm not going to be talking about any models. I'm not going to be talking about geothermometry or MT. I'm going to be taking a step back, because I'm also not a diplomat. So I will say bluntly, there's a lot of challenges, not just about the resource in Taiwan. There are challenges at every geothermal field that need to be overcome, but more fundamentally of the approach that the community takes here to solve those problems. I am a strong advocate of innovative science and engineering practices, but you have to get the fundamental geoscience best practice approach in place first. Because if you think that you're going to drill EGS holes down to 4, 5, 6 kilometers, when you already admit that you have great difficulties drilling conventional geothermal wells, and debate where we will site those wells and the spacing, and the gentleman from the Philippines this morning made a very valid point that a lot of people, I hope, heard, you're going to continue to have problems. And they're going to be problems that are almost insurmountable problems. And the New Zealand delegation is here this week to help you find solutions. And that's what it's all about. So I apologize if that sounds very direct, but I'm very passionate about geothermal and I want to see you succeed. So the geoscience objectives are to identify available geothermal energy, to characterize the resource, to identify possible challenges, to delineate size capacity of the system. to provide information for baseline environmental assessments, to support strategic decision making, to support future management decisions and operations, to clarify resource risk, and if necessary, to withdraw from an unviable project. You need to invest in your geoscience. Geoscience should not be seen as a cost that is detrimental to the project. It should be as a strength that takes your projects forward. Do you mind closing the door, please? The provision of geoscience is ongoing, and it has greatest value from the integration of all data from all sources, both past and new data. You need to look critically at those results and combine those findings from diverse investigations. So I know in Taiwan it's very advantageous to draw on expertise that sits in many different institutions. But you need to be able to use the geological influence to support the geophysics, the chemistry information to support the geologists. Now, if those institutions are discrete and separate and not communicating, then that is not effective use of the resource that already exists in Taiwan. You need to consider the physical chemical processes in the geothermal systems and how those insights inform the commercial operations. We are not in this room and we are not developers of geothermal resources for academic reasons. We want to have a viable, strong industry that is making money and making impact and supporting communities. We need to promote frank conversations with stakeholders, partners, and communities, including indigenous communities, concerned with the sustained use of the resource and how effects are best managed. And that is not clear if you don't use good science and use it in the right way. You have to start with a robust survey design and use best industry practices. The surveys are conducted to address specific issues or uncertainties. So when you are designing a geophysics survey, it needs to be answering specific questions or uncertainties about the resource. You are not just box ticking. If you do a gravity survey just because we need to do a gravity survey, you're wasting your money. It needs to have a purpose and needs to be integrated. Results may sometimes be ambiguous. No, I'm a scientist. That's good because that prompts me to ask questions. Why are those results different? What is that telling me about the resource? Information always provides new insights, and those inconsistencies and discrepancies must be integrated into the understanding. It's really important also to not over-interpret the data or present results in a way that meets predetermined wishes. So it's difficult sometimes for a junior scientist to present bad news to their boss or those people on the 13th floor. But you have to do it because you have your integrity at your heart. And always challenge the data. What does this mean? What is it telling me? In that way, you'll have a better understanding of the dynamics of the geothermal system, and you will be de-risking. Good communication, and there was reference this morning with some of the drilling about having good communication. That can be in the office, in the field, at the rig, and it's necessary for all the geoscientists that are in this room to speak up, have a voice and influence the decision-making process. You may not be the person that makes the decision, but you have an important role in influencing that decision for the benefit of the project. Provide clear, unambiguous advice, clarify uncertainties, and also work within financial limitations. Be conscious to the audience. Be informed, be respectful, be honest, try to avoid alarmist language, or we're going to have subsidence. Well, that's alarmist. Try to avoid those statements. There's also, from the communication aspect, communication is a two-way process. So good managers need to listen to geoscience advice. You need to challenge the scientists to deliver on agreed objectives. And we know that in many cases they may be difficult for geoscientists to answer questions. But challenge them. Challenge them to find solutions to those difficulties. Geoscientists, as I say at the bottom, are naturally inquisitive people, but you need to support them to stay focused on their objectives. Because as I say, this is not an academic exercise, this is for commercial results. And I may have sounded pessimistic, and I apologize for that. I think there are many things that Taiwan are doing very well. You have identified prospects. You do have geothermal potential. You have a very knowledgeable geological capacity here in Taiwan. Very competent, very highly regarded scientists in chemistry and geophysics as well. Mostly in academia, but they are well placed to support the aspirations of government and industry. You're very enthusiastic, but you are less experienced in science capability in the industry. And I believe that there does need to be an investment within the industry to expand the geoscience capability, because that will de-risk. There's a lot of good quality science data, and that needs to be continued to be assessed, be publicly available to support the exploration, in which cases you avoid repetitive surveys. And I have been involved in projects in the past where the repeat survey with the repeat technique has been conducted at the same place. And for me, that needs to be thought through better. There are some things that Taiwan can do. As I say, geoscience is often seen as a luxury, and the survey designs are compromised by financial constraint. But an investment in the geoscience will pay for itself in the long run. So make it easier to conduct surveys, because they will support the exploration and development. Use best practice. So in the space of drilling, New Zealand has developed a best practice guide for deep geothermal drilling. This expertise sits internationally, so take advantage of that, because that will be beneficial to you. Geoscientists appreciate the need to work within commercial limits and to justify new or expanded work of value. So you need to continue to integrate international expertise to build the capability here in Taiwan. So in conclusion, every geothermal system is different, and each requires application of unique geoscience solutions to resolve system dynamics, to optimally target wells, and to de-risk exploration. The scientists and the managers all need to challenge the geoscience. You need to ensure that your geoscience is built around robust survey design, strong, consistent acquisition protocols and data processing, and then interpretation and integration of results from all disciplines. And at that point, when you have confidence in the data, when it's been collected well and processed well, then pass it on to the modelers and the visualization modelers and the numerical modelers, because their models, and it's been suggested all models are wrong. I am not in that camp. I think all models are influenced by potentially wrong data. So avoid that situation. We have some terrific tools. How did Wairaki be developed? Kamajang, Tiwi, when we didn't have any of those models. The reason was because we had good scientists and engineers doing the fundamentals well. The tools that we have now, the modeling tools and numerical tools, make it easier. So move forward with that in mind. So it's for Taiwan to continue working towards easy access and sharing of geoscience data, and to support human capacity building in geothermal science and technical areas. And just in conclusion, I'd like to thank two companies that sponsored me to come to Taiwan again this week, Nikiso and JRG Energy. I would stress that the opinions are expressed are mine, and also to the Taipei Economic and Cultural Office for their support of the New Zealand team. And please come to our session this afternoon, and you'll have an opportunity to fire criticism back at me. Thank you.
Thanks, Greg Ganel, and thanks again your wonderful big advice for Taiwan. And sorry, we are less of time, so we maybe come to next topic. Thank you. And reducing drain risk through effective geochemical assessment. Welcome the Ali Farouzi, Mr. Ali Farouzi. Thank you.
Yeah. Good morning, everybody. I'm happy to be here to deliver the presentation, Reducing Drilling Risk Through Effective Geochemical Assessment. My name is Ali Farouzi from Thermochem Indonesia. Thermochem is the world leader testing in engineering, consulting services, and laboratory services. We provide services from exploration, development, production, manufacturing, sampling, geochemical analytical services, well testing, geochemistry and production, including in the production pH modification and so on. This is our worldwide experience. We will bring our perspective from our company that based in US, Santa Rosa, and Indonesia to Taiwan. So this is an outline of the discussion. The background is Taiwan is an island nation that mostly depend on power import of power generation, but geothermal is one of most important energy resources in this country. So the potential up to 30 gigawatt or more. Last year, the capacity only 7.4. Compared to Indonesia, the world's second largest geothermal producer in the world, we have installed capacity 2,742 megawatts. Why the installed capacity is so low compared to the potential? As you see in this graphic, that in the early stage, the surface manifestation or 3G survey is risk is very high, but the low is very cost. The cost is very low. But drilling, exploration drilling, production drilling until the power plant is high, but in the cost, but risk is very low. So it's important to us to know to conduct the survey, the 3G survey, including geochemistry, because the cost is very low. To reduce the cost, we have to know more, to gather more data about from 3G, including the geochemistry. So we do assessment, review, no or no go, reassessment again, review again. Uh, Next. So the limitation is reducing drilling risk on early stage of exploration stage prior to drilling, because after drilling we know the fluid characteristic from our reservoir. So as I mentioned before, the exploration is very cheap, the drilling is more expensive, but maybe everybody jump into drilling to test the reservoir before we know more data. Uh, we know the characteristics of our reservoir. The high quality data that you have, the lower risk you get. To assist in locating good drilling area prospect, the surface manifestation is the key, and geological structure also is another key. So don't neglect it. To understand the geochemistry and mitigate the risk, we also to know the Taiwan tectonic evolution. Taiwan represents an active continental collision between the Eurasian plate and the Philippine plate. Ongoing collision has built a young and rapidly evolving mountain belt across the island. Within the system, the central range represent the metamorphic core in the southern and volcanic arc in the northern. So this is the volcanic arc in the northern and metamorphic or rock in the southern. Will emphasize both geological setting. In Indonesia, and Montalang that have a magmatic volcanic type, but we are proposing the system to convective geothermal system and also young system. But young system is very high NCG, magnetic input very high, and no chloride boiling. So we have to understand the signature of chemistry in our geological setting or in our place. There is no chloride spring in convective. There is a chloride spring in fiber core. The fiber core or neutral liquid and paired with neutral liquid reservoir, there's the gassing magma. The gassing magma have chimney in here, but no, but there is a neutral chloride here. Compared to here is only one fiber core, but this is a fiber core with boiling zone here. So we drill here, so we will know the proposed geochemical model from geochemistry also. So this is the signature chemistry. There is a chloride spring, chloride sulfate spring. The helium isotope also show the volcanic arc. So from geochemistry, we will know the fluid flow, everything about the characteristics of reservoir. So this is combined with geophysics. We have perfect the geochemical model, so we will know the good area to drill. So in the metamorphic high gradient temperature, but the pH brine neutral to alkaline, carbonate rich, CO2 rich. So in development risk, we have the calcium scaling. In volcanic arc, we have acid fluid. So this geochemistry objective is estimating reservoir temperature and boundary system. We will know the boundary of the system, where is the fluid, where is the outflow, to reducing the risk of drilling a cold, dry, dry well, no heat, no water content, or low temperature or unproductive well, or identifying the reservoir fluid characteristic or and origin of thermal fluid. We will know the acid fluid, high silica, high salinity, carbonate rich or neutral fluid, or combination of those fluid. So to preventing costly about the casing failure or wellbore scaling. Also to locating the outflow zone and the fluid pathway, we will know the high temperature, most productive area, the process, it is secondary boiling or direct from heat source. We will know everything from geochemistry. Also to distinguish the reservoir type. Drilling technique is different for steam cap only, for liquid or steam dominated. So in this case, in the Sarula that have acid fluid, but the geochemistry propose two model. The second model, the most likely model is secondary condensation, oxidation of H2S mixed with natural chloride from reservoir. Next is monitoring during drilling. The geochemical can predict the acid fluid, of course, corrosion. High gas, we need a H2S abatement. Silica or calcium scaling, we need the operating in good way, or good fluid incursion. So we will know how where to put the production casing, how to put the production liner. So to build the conceptual model, there's this uncertainty. The blue one is uncertainty. From geochemistry also, we have an uncertainty of outflow, and reservoir boundary. But this is, we will know our geochemical conceptual model, but with uncertainty. After that, we can study of analog field from other field. Data quality and assessment, the geochemical collection of geochemical data with proper method and good quality. We need like water analysis, gas analysis, stable isotope, helium isotope, sulfur isotope, carbon isotope, including the radon-Toron survey if we need to support the geological structure from a geochemical perspective. So in Lahindong, the best study in Lahindong that the acid here, but there is a structure, the impermeable structure, and they drill the acid and they also drill the neutral chloride side by side well. So this is important to know how about the reservoir, our reservoir fluid. High quality data is used to make important to make important resource decision. So this is our lab capability. We can do everything about geochemistry analysis. This is also we have to concern about the feature priority. If you have a lot of budget, we can do we can collect everything about thermal feature. But the ranking of usable thermal feature is from by number one is neutral chloride. This is the list of analysis or collecting sample. Different analysis, different collecting sample. Different analysis, different method. This is the moderate priority. This is the lower priority. As you can see, this is in B2, Tatun. Last year we have the project to collect the complete geochemistry assessment in Tatun. We collect gas, including this lower priority, because we will know we can model the fluid pathway and the process from the reservoir to surface. So also we have data quality bottle prep. For each analysis, we have to treatment the each analysis. with each chemical preservative. So this is the brief of sampling method. This is gas sampling. Sometimes just simple, but need to good way or proper way to conduct the sampling. This is gas sampling on formaldehyde, on solfatara. We use the bottle for total NCG, carbon isotope, sulfur isotope. Which metric we use, gas or water, is different method also. For us, safety is number one, but data is also a priority. So, this is gas sampling on bubble spring. This is SO2 sampling. We have to know the magnetic input of SO2. We use like a copper tube to collect the helium isotope. This is water sampling. Find the high temperature, collect the fluid from main source, not mixed water. So this is also carbon isotope. We have the special container to conduct the sampling of TIC water. We have to also concern about the data quality. Water sample result is correct. If bad, is coming from the technique of collecting the sample or bad in analysis. So the ion balance is one of data quality that we have to concern about this result. The ion balance should be low, 5%. So in data quality of gases, we use like CDCl to prevent the oxidation of H2S, to know true value of NCG content and each of gases. This is our lab result and NCG and water. So we will know everything about gas content. We also provide some concentration in different concentration. Conclusion from geochemistry, we will build the geochemistry conceptual model. So we will have fluid source, reservoir phase, liquid level, temperature contour, reservoir process, including the reservoir fluid chemistry. If we know everything about our geochemical model, we will combine with geology and geophysics. Thank you.
Thanks, Ali Faruzi. Thank you. And we go next. The Taiwan drilling experience. Mr. Francis Bang. Thank you.
Morning. My name is Francis Bayon. I'm with Baseload Taiwan. And today I'll tell you a short story of Baseload Taiwan's first geothermal drilling experience in the country. So the main purpose of this talk is really to share the experiences and, more importantly, the lessons learned from that drilling campaign. It was a one-well drilling campaign. And hopefully our colleagues in the Taiwan geothermal industry can pick up a thing or two and, make things a little bit smoother for everyone moving forward. So this is a quick, this is just the outline of the talk. This is not going to be a very technical talk. It's going to focus on the problems that we encountered and the lessons learned consequently. So we drilled well RS V101 in Ruisui in 2020. We spudded the well in 2020. We completed it in 2021. Drilling was essentially based on a review of existing well data in the area, and the picture on the right, it's not very clear, but it's a plot of all previously drilled wells in Ruisoy. Unfortunately, the data available to us at that time was not as comprehensive as we would have wanted it to be. So, but anyway, we drilled the well, and then after drilling, well, the well is V101 is over here, somewhere over here, and these are the other wells drilled in Ruisoy. So after that that drilling work, we decided to step back, as Greg would say, and do our own surface exploration. So we did 3G work in 2023, geologic mapping, the geochemistry survey, and the okay, thank you. All right, thank you. I don't have this at home. Thank you. Okay, so we did geophysics, gravity, and MT. And at the end of that exploration work, we came up to the general conclusion that the resource is good for between 4 and 30 megawatts, depending on who you ask. Okay, so this is the well was spudded on August the 14th of 2020, completed July 1, 2021, and I'll obviously I'll tell you why that is. TD was at 1264 meters. This is a vertical well. The highest, so on the left is the casing profile. We drilled the 17-inch hole and run in the 13/3/8 casing down to 204 meters, roughly. We drilled the 12 and a quarter, and run in the 9 5/8 casing down to 671 meters. And then we drilled the 8.5-inch hole down to TD 1264. We run in the slotted liner, the 7-inch slotted liner, down to that depth. You see the picture on the right, that is the temperature profile of the well. The highest temperature was recorded at about 175 degrees at around minus 400 meters elevation, which was what? Like 500 meters depth. So effectively, we cased off the highest permeable zone, the most permeable and probably the highest temperature zone of the well. We ran into some problems. We had a blowout while we were running in the 7-inch liner. We drilled the open hole in heavy mud. We had, unfortunately, a very, very short flow test of 1 to 2 days. This is not common and not ideal in a geothermal setting. As I would tell my colleagues, we should be doing flow tests of at least a month. It can't be anything shorter than that. Anyway, we did a very quick flow test of the well. So these are just pictures of the pad and while we were preparing for drilling. So the construction of the cellar, on-site drilling preparations, and then we were rigging up. Okay. The figure on the left is day versus depth curve. The well was originally planned to drill for 40 days. We ended up completing the well a little shy of 280 days. And we have a very long flat spot in the 12.5 section. So in the 17-inch section, we were originally drilling 24 hours for the first few days. And then we ran into some issues and we had to stop 24-hour drilling and just work 12 hours a day. That was the first problem. And then so these are just statistics on each section. 12. So we started at 12 and a half section, 12-day shifts, 12-hour shifts only, and all the way to TD. And again, those are the casing setting depths. But yeah. Okay. So what problems did we encounter? In the 17-inch section, we had to do remedial cementing when we were running in the casing because for some reason, when we were doing the primary cementing job, the plug did not release. So we had to redo it, remedial cementing slowly, and that took us 3 days. Like I said, in the 12 and a quarter section, we were drilling 12 hours a day only. So at the end of the day, at the end of the shift, we would pull back to a certain depth, circulate, go home, come back in the morning, circulate. You know the drill. And then when we were running in the liners, or sorry, the casing, we experienced a blowout. So we had to deal with that blowout, and it took us another 5 days. After we run in the casing, hang on. After we run in the casing, we had a fission hole. We dropped the BHA. The BHA slipped through the slips. So we had to do some fishing operation. And unfortunately, there was no contingency on fishing. So we didn't have any fishing tools on site. We didn't have, I don't think we had contact with fishing operators outside the country. And so when we needed fishing tools, we didn't have a number that we could call and say, hey, can you bring in your fishing tools? We had to go through the directory and look for a number for the fishing services. And please remember, this is in the middle of the pandemic. So the logistics of bringing in tools from wherever was a nightmare for everyone. So that took us 132 days. And then again, we had so when we finally got the whipstock, we sidetracked the hole. When we sidetracked the hole, we cased it off at about 670 meters. In the 8.5 section, we also had another stock pipe, and we were successful in fishing the thing out. So, but the whole section was drilled with heavy mud, primarily because of the blowout that we experienced at the lower level. So, to sort of control the wellbore, the drilling was done with very heavy mud. I can't remember the exact mud weight, but believe me, it was heavy. Okay, so issues. Number one, 24/7. No 24/7. And all the drilling experts in the room will agree with me when I say that drilling, especially drilling problems, are very, very time sensitive. If you have a stuck pipe at 6:30 in the evening, you can say, oh, it's almost knock-off time, let's do this tomorrow. You can never do that. It will just, it'll just get worse and worse. So the quicker you try and solve the problem, the better for you. So that was the first, that was in terms of the delay. So equipment and logistics, we did not have any fishing tools, no contingency for fishing. So we had to do it from step one in the middle of the pandemic. Oh, sorry. During operations, the rig had 2 pumps. Most of the time, 1 pump would be down. So we were effectively operating with only 1 pump. So that also slowed things down. The technical trade-off for for drilling with heavy mud was that you sort of closed whatever permeable horizon there was in the open hole while you were drilling. And that was verified and confirmed when we did the logs after drilling. The skin factor of the well was plus 15 or something like this. This is the first time I've ever encountered a plus 15 skin factor, but yeah. And then we had, we were very reactive. So the first key learning, and this is really a base load key learning, get your fundamentals first. Greg was I agree 150% with you, Greg. Do your geoscience, do your exploration, get your model, so that then you define what your drilling targets are. We also had issues with handovers, especially because it was only a 12-hour shift. So we would have issues with that almost every day. Stakeholder management. So we went from 24-hour drilling to 12-hour drilling in a matter of days, and we had to do 12-hour drilling the rest of the way. And I said, it's not ideal. Planning, again, the contingency for fishing, contingency for sidetrack, things like that should have been considered, and at least you get a phone a friend number at the very least. The equipment, the mud pumps had issues. The slips were obviously not inspected regularly, and that's why we had that failure. And then we had the last is essentially on decision making, because this was a turnkey contract, not a day rate contract. And with a turnkey contract, I mean, we had our company man on site, and he would suggest to the drilling contractor what he thought was best. But at the end of the day, because it's a turnkey contract, the drilling contractor would do what he thinks is best for him to achieve his objective. So it's, in terms of more operational control, it's really better to have a day rate contract rather than a turnkey contract. And I'm done. Thank you very much.
Thanks, Francis Bayong. You are sharing your pressure experience drilling in Taiwan. Thank you. And we go next. Reducing drilling risk with 3D reservoir models. Claire Buster, thank you. Miss. Thank you. Thank you.
Thank you. Kia ora and good morning. My name's Claire Baxter. I'm from Sequin, and we develop those modelling tools that everyone has been talking about today. So can I get a show of hands? We're getting towards the end of the session, and I'm aware people haven't been moving. Who here has heard of Leapfrog for 3D modelling? Many of you. It's good. Sequin are the developers of Leapfrog software, as well as other modelling software too. So we provide the tools that allow you, the geoscientists, and the data analyst to communicate and to further analyze those tools of the subsurface to gain greater understanding. An example of this is from Fervo Energy. So we've heard a lot about a variety of different technologies for geothermal. Our tools are used in all of them to test and to analyze if it is a viable option to go forward. And in Fervo Energy's case, the modelling tools allowed them to deliver 100% well success. But this not only started, out of thin air, as Greg and Francis have mentioned. This started of many, many years of data analysis and understanding first, plus the joint collaboration with the knowledge of a variety of different people, as we have here in the room, to generate good quality models that they can then base their decisions from. So when we start looking at 3D models, I can tell you Sequent works with companies that make up 70% of the global geothermal power capacity. And everyone who I've spoken to in my years traveling around and working with those organizations and developers, that they've said moving from 2D analysis into a 3D world has enabled them to decrease the risk and to increase the success of their wells. And the reasons for this is they can better validate and analyze their data. They can create faster models, which enables them to create a wider range of different models, such as your geology, your structure, understanding seismicity, geophysics, geochemistry, to enable better decisions from a greater range of data. And it also allows that collaboration and communication of that understanding to the wider stakeholders that we have to enable those decisions, including those expert peer panels that are going to critically analyze and question your decisions to ensure the best success possible within your project. If I can take 3 examples where we look to validate and analyze our models, I want to go to Japan for the first one in the field of Abino. In 2017, they took 20 years of production data and downhole information to re-establish the conceptual model. They spent hours scrolling through Excel spreadsheets trying to ensure that they had quality data going into that model. The minute it came into a 3D environment, within seconds, they could see that they had a 300 degrees C temperature point a couple of meters below the surface, an obvious error within their data. So something they didn't pick up within 2D, within Excel. We can also use Leapfrog to give our data a voice, to try to understand that data better and what it's trying to tell us of what's happening in the underground. We go to Kenya, to Menengai, GDC. They drilled 35 wells of their field, Menengai. Initially, they thought Menengai had one upflow. They did isotherms within Leapfrog, allowed it to interpolate and do its thing, and straight away you could see that the data was telling you there were 2 upflows within the system. This started the process of them questioning what was actually going on so they could deep dive further into the other data that they had to try to support that new conceptualization. And finally, we have the capability to start building multiple different, or to test different understandings and ideas that we have of what's going on within our field. So when I did my thesis on numeric modelling under John O'Sullivan at Auckland University, I looked at the Azores in Portugal and the Pico Alto field. There, we thought their outflow may be inside the caldera, maybe on the side of the caldera, or maybe just outside to the southern part of the caldera. It was numerical modelling using Leapfrog and Tough at that time that I ended up concluding within my thesis inside the caldera was cold and that the upflow was happening towards the southern part of it. The company there later drilled into that caldera, and as they passed through the fracture of the caldera, the fault upflow of that caldera, they saw it as a barrier, and it was cold on the other side, corroborating what their study has shown. And so we create different, or we analyze a whole range of different data sets. And I think we've already heard from many different speakers some of those. We want to understand our drilling hazards. We want to understand the geology. We want to understand the fracture, the microseismic network. We want to understand the temperature and the feed zones. We also have challenges at the surface. I know here we only have the capability to drill with where our leases sit and our lease boundaries go down within the subsurface. Or you might have exclusion zones like we do in New Zealand to protect our taonga and our treasures. And so what we're starting to see, such as what Pertamina did, or PT Pertamina did from Indonesia, is they applied a play fairway analysis technique within Leapfrog, where they took and built 10 different models, all ranging from different analysis, as you can see here on the slides, and they created a favorability map for their well targeting. So you have the outputs here in the middle within the image. That allowed them to say 50% or create 50% time efficiency in the exploration well targeting program in time. We're still waiting to see the successful nature of those wells and how they went within drilling. So hopefully this year or next, we'll be able to come back to you and hear how those models helped. Models are not an isolation thing. And once again, I think what we've also heard continuously over the last 2 days is the development of a geothermal field requires many expertise, both locally and internationally, to come together. Everyone within this room brings knowledge, different knowledge, that you can share and collaborate to make the best decisions for the different fields that you're looking to develop. And it is standard practice that we often sit within a room, spend a week or a couple of months collaborating and discussing amongst each of those peers to make the decisions of which wells out of the maybe 20 or 25 options that we've been presented, so that we drill the best targets and can develop those fields. But then we also have the component of expert peer review of those models. And it's through the visualization and the communication that Leapfrog brings that we can then share their understanding and communicate their understanding very clearly with the other experts. Our tool Central in model management allows us to track each of the decisions and the journey of their understanding and iterations within the models, so that once again we have a clear pathway of how those decisions have been made and a clear communication way that we can communicate onto and share with the wider communities as well as experts to support and corroborate those decisions. The two speakers before me took the words out of my mouth. You know, we've already heard this saying is something very common when we talk about models. But I agree with Greg and I agree with Francis. Models can be very accurate. And once again, we have examples where this is the case. Where they are accurate is where we're taking time to analyze and to understand what the models are what the data is trying to tell us. We're ensuring we have quality data going into those models. And we ensure that we put our knowledge from a variety of different experts into those models to make the best decisions. To give you an example of where it can be right, we can go to the UK, where there was a Leapfrog model done from historical mined workings, where they were looking to mine the heat within the water of old abandoned coal mines within the UK. They were 400 metres off in the Leapfrog model to what they drilled. So you start thinking around the distances that Kenway was talking about within the drilling rigs and how far they go. This is how close you can become when you start incorporating as much detail and knowledge as you can into that model. But at the end of the day, the commercialization of geothermal comes to how we can sell it, in electricity or as heat. We need to understand what the resource can produce at the surface in order for us to make an economical model. And so it's with Volsung that enables us to build these coupled wellbore models where we can understand and model the numeric changes that are taking place in the subsurface, how that fluid is flowing up the production well into the power plant, and then how it's re-injecting back down. This not only ensures that we're testing out from the well target that we've placed in Leapfrog what the actual power output's going to be using Volsung, but it means that we're also creating sustainable decisions so that the geothermal reservoir can be long-lasting for many generations to come. And so it's with that, if you do want to find out more around how Leapfrog, Volsung, or Central can potentially help you, and you can use them as a tool to support the development of your fields, please scan the QR code to find out, or alternatively, talk to many of the experts who use that tool, many whom are here today from New Zealand, like JRG Energy, Earth Science, Greg, University of Auckland, as to how they have been applying those tools to develop many fields around the world. Nō reira, tēnā koutou, and thank you for your time.
Thanks, Ms. Claire Buster. And we can have a question, one question. Okay, please.
And can I ask the lady about you have mentioned about 10 megawatt output from a single well is possible. So do you have any experience, actual one well output 10 megawatt operation?
It all depends on the field and the resource that you have and what you're drilling. The example that I told you was the example from Fervo Energy in the US. So they are the company who used advanced models to drill and to obtain 10 megawatt from their well.
Thanks again. Thanks. Okay, let's go to the last topic. The mapping far-field natural fracture in geothermal reservoir using sonic image. But today the Florian Carpenter is not come here, so we the Tito Stacker Putra Perdam. Sorry. Thank you. And he say no question. Okay, please, thank you.
Thank you so much, sir. Morning, all. As you know, Florian Carpenter is definitely not my name, right? My name is Tito Perdana. I'm a senior geologist with Geothermex SLV. And today I'm representing my colleague, Florian. He cannot make it today because he had some emergency. So he had to fly back. I don't think I can. Yeah. You can hear me well, right? Okay. So, okay.
Must use the microphone, please.
Okay, sure. Sorry about that. Okay, so I'm representing Florian because he had some emergency and he had to fly back to Malaysia. This is not my expertise. This is beyond my expertise because I'm a geologist, not geophysicist. But I'll try my best to convey the message from Florian. Okay, so the topic of today's presentation is mapping far-field natural fractures in geothermal reservoir using sonic imaging. As you know, understanding subsurface structure is very important in any geothermal fields, right? Especially in Taiwan, Indonesia, the Philippines, where fractures play a very important role. And nowadays, finding permeable structures is so difficult. It is very challenging. I've seen this anywhere, Indonesia, the Philippines, Taiwan. So that's why this topic is quite important to understand, subsurface structures development. Thank you. Okay, as I mentioned earlier, fractures are very important. Let's talk about Taiwan, right? You go to Tatun in the north. It's a volcanic setting. So our target is fractured andesite. You go to the east, the metamorphic setting. Our target is fractured metamorphic rocks, especially Lushan formation, right? So understanding fractures and faults are very important. That's why I've been telling my clients, we need to have a robust geologic map and cross-section that will help us to understand the geothermal system. And once we have this good geologic mapping, we will integrate with geophysical data as well as geochemical data, as presented by previous presenters, right, to understand the system and to find the sweet spots. And once we have the target, we will drill. But right after drilling, we also need to get data as much as possible, especially to understand the subsurface structure, right? So that's why some of our clients, they will do wetland logging to understand the subsurface using borehole image. There you go, right here. The borehole image, the depth of investigation is very shallow. It's about 1 to 2 centimeters from the borehole wall, but it provides you with a high resolution image. You can get open fractures, you can get closed fractures, their orientations, and their distribution, right? But because geothermal wells are drilled mainly by water-based mud, so open fractures, usually like a conductive or black color features like this, they can mean two things. Number one, they can be open. They are filled by mud, by the drilling mud, or they can be closed if they are filled by pyrite or clay minerals. So that's why some of the clients, they also run the dipole shear sonic tool, sonic logging tools, to understand whether the fractures that they see from the electrical borehole image are actually open or closed. They combine together. And the depth of investigation of this sonic log is about 1 to 2 meters beyond the borehole wall. And if you want to go all the way to about 1 kilometer, there's a new method called walk around VSP, right? There's a one receiver in the borehole, and you put all the sources, walk away from the borehole to understand the structure development away from the borehole. It's about 1 kilometer. And what I'm talking here now is something between this one and this one. That is called the far field sonic imaging, that will give you the image of something about 50 meters away from the borehole. Why is it important? Let's say if you have a hole, right, a borehole, and there are several fractures that are being intersected by the boreholes. How about fractures that striking parallel to your borehole? How about fractures that are quite vertical, that are not intersected by your borehole? And those fractures can be very important. We don't want to miss this information, right? That's why we have this new technology called 3D far field. So basically, this is the sonic tool. What we do here is we usually focus on the borehole, inside the borehole, but there actually one sonic energy that goes all the way, beyond the borehole, and once it touches a different impedance, acoustic of rocks, or big structure, it will be recorded in the receiver, and that will give something like this. It's like, you know, time and distance. So it gives you all the wave. So we have compressional, shear, and then stonally, right? But what we want is something that is beyond this. So the new processing method is to minimize the borehole effect, and that will give you this nice 3D far field. And then again, each of these events, we will process it again. We will further process with ray tracing and 3D STC, and that will give you, you know, a clear picture of this pattern around your borehole. But again, because it only, you know, records the events, as a geologist, we need to understand what caused that. Is it because of the bedding, or is it because of structures? That's why understanding geology setting of the area is very important. Okay, this is one example from Japan. So this tool, the sonic imaging tool, was run in a geothermal well in Japan, right? And then they also run borehole image. So they compared the results. And what they found is, you know, the far field fractures is about 30 meters from the borehole. They have similar orientation with the resistive fractures from the borehole image. So it means that the big fractures that are captured by this method are actually closed fractures. They are not open. That's why combining borehole image and sonic far field is very important. The next one, this is from Utah, right? This is quite interesting. So the borehole image, you know, they recognize a lot of fractures development. And what we have here is, this is from borehole image. The fractures are striking northeast, southwest. But what we found here from the 3D far field is not just northeast, southwest. They also found something different that is northwest, southeast. These northwest, southeast fractures, they are not intersected by the borehole wall, but they are recognized from this new method. There's one other example from Middle East. It's quite similar. There are several fractures intersected by the borehole striking northeast, southwest. But after they ran this, they found something northwest, southeast. And it turned out that the northwest, southeast orientation is very important. They are all open and permeable. So the conclusion is, you know, characterizing subsurface structure is very important in geothermal project, right? And then combining all the data from surface mapping, you know, borehole image, 3D far fields is very important to understand the whole picture of your structure, because this will help you to develop your fields better, and also to help you to place your next exploration well or your next development well in the field. That's all. I hope you enjoyed the presentation. And I'm so sorry because this is not my expertise, but I hope I can convey the message from Florian quite well. If you have any question, please feel free to contact me at any time. Ching An, do you want to say something? All right. So Ching An is here. He is the wetland expert. He is based in Taiwan. So if you have any question about the wetland logging of SLB, please feel free to contact Ching An directly. Thank you. Thank you very much. Appreciate it.
Thank you. Thank you, everyone. We have covered all the items on our agenda for today. Before we vote up, I'd like to sincerely thank you for all your time and active participation. I know how busy your schedule are, so I truly appreciate the energy and the great idea you brought to the table today. Thank you. And I'm sorry we don't provide lunch today. Therefore, I thought you can treat a meal to the speaker whose presentation you are most interested in. And so, thank you once again for your hard work. However, have a great rest of the day. This meeting is now adjourned, and through your help, may geothermal activity can take great advance in Taiwan. Thank you. We finish. Thank you.